also very, very pleased again to introduce our third speaker, Professor Themis Bowcock from University of Liverpool. And the title of the presentation is on ABC of CPT, a look through the mirror. So we look forward for Professor Bowcock's presentation.
Okay, thank you. Okay, thank you very much. Thank you very much to the organizers for inviting me here. I'm going to talk a little bit today about CPT. Now, obviously, CPT is a very complicated subject. It's not something that we're going to understand instantly today, and it's certainly not going to understand it instantly from my talk. I'm really a detector builder, so I'm going to give you a somewhat prosaic description of this, but still, I hope to give you some idea of the concepts and the history, and perhaps spend a little bit of time how to look forwards about how we're trying to understand these things. So just a personal comment, what motivated me as an individual to try and get into the field of physics was some very, almost childish questions, like what happened very early on in the universe, and I've spent a lot of my career about trying to understand why there's a matter-antimatter dominance, one over the other, and I've built experiments, or build experiments, at least partially, to try and answer that question. As part of this route, what motivates me, not being clever enough, what motivates me is I like to build equipment, and hopefully we'll discover something that some really smart guys in this audience, and you're going to hear from some of them later on, who are real experts in this field, can actually explain and shed light on the subject. So all of you know, or probably all of you know, otherwise you wouldn't be here, there are essentially four forces in nature as we know right now. Most of them are combined together, especially the strong, the electromagnetic, and the weak, and that's where I'm going to concentrate my talk today. And of course, you also know that within the context of that, there are a whole bunch of fundamental particles, elementary particles as we call them, split into the quarks and the leptons and some other particles that mediate these forces. And these quarks especially are going to come into play early on, and I'll tell you something about how we also use leptons to look at CP later on. One of the most important things, and I'm just going to put this out there, just lodge it in the back of your minds, the weak force has a very special property that some of the quarks, these fundamental building blocks of matter, can actually transmute from one type of quark to another type of quark, almost interchangeably, and this is something that's going to play an enormous role in our understanding of the phenomena. So, the symmetries I'm going to talk to you about today, as advertised in the talk, you'll hear more about this from Christina later on, are the CPT, CP and CPT, and I'll try and explain to you what these all are. Essentially, we have three basic ones, CP and T, and out of those we form some composite symmetries afterwards. And having said that, let's get straight on with the first one, the C. So C stands for charge conjugation. In the easiest sense, you just take a plus sign, change it to a minus sign. With a little bit more sophistication, we actually understand C as taking a particle to its antiparticle, and then seeing if physics stays the same under that exchange. And of course, if I take a particle to an antiparticle, I immediately get involved with the problem of matter and antimatter. And for those of you who don't delve into this day in and day out, antimatter is not something that's completely strange and out there. There's a lot of it around. In fact, as you're sitting here in this building, there are about 10,000 antiparticles going through you every second. If you go to a hospital where John Radcliffe, of course they used to bring one of these here at the John Radcliffe, it's actually used in PET scanners to diagnose what may or may not be wrong with you. And if you especially like fruit, even some fruit give off antiparticles. So it's here, it's all around us. And for me personally, it's quite interesting to think, and okay, this is a quasi-philosophical statement, but of course, we know that if you had the same amount of matter and antimatter, it would probably be less easy for us to exist. So this matter-antimatter symmetry is of profound importance to us. As we go through this talk, one of the things you'll see is things aren't as simple. You know, we tend to think of billiard balls rolling around, I'm going to flip the signs and so on and so forth. When we're talking about empty space, actually, It's a dynamic thing, full of everything you can imagine, all the different forces, all the particles and antiparticles, and they're all sort of swirling around, matter density changing. And when we do our experiments, we actually sort of probe all these things at the same time. So you can't ignore these higher things. And we'll see this when we come to the precision measurements of these weak particles. We start to become sensitive to this sort of soup that's all around us. So I've talked a little bit about C, en passant. P is a p parity where you flip r to minus r, and just to be clear, this is not the same as some infinitesimal r transition. This really is flipping r to minus r, and again asking the question, does physics stay the same? And normally when people talk about this, they start to talk about mirrors and looking in the mirror, and is everything the same? It's not the same, right-handed, left-handed. I'll just point out here that if you do look in a mirror, of course, what doesn't happen, and if you have children, they may have asked this question, is you don't see yourself upside down. And you have some explaining to do, and that's because the mirror isn't really doing parity. This is a picture of a mirror. If you cut out a word, put it in a mirror, you'll actually read the word back properly, which is not what you think is that you'd see. If you really want to do a true parity inversion, you actually have to use a clever little piece like a prism retroreflector, and that actually will do the job for you. So don't sit there starting thinking about right and left mirrors. That's always a little bit too easy. R minus R is tricky. And then the last ingredient is time reversal. And thanks to Helen Quinn, this is, of course, this was known before, but she's in a nice little talk at this conference, she specified 3 different types of time asymmetry, a universal time asymmetry, and she referred that back to the very earliest universe and inflation, saying clearly things weren't the same forwards and backwards. And we're not talking about that here today. And we're also not talking, unfortunately, because it's probably quite interesting, about the arrow of time or psychological time. We're actually talking very specifically about microscopic time asymmetry. And I don't really have time to go into that, but that's how microscopically the laws and the equations that govern the dynamics actually change under time reversal. And of course, once we have C, P, and T, you can take a square, orange, or a blue box, and you can try and break it up into different components and say, this is a blue box. You can try and talk about C and P and describe them as sort of composite things, or even C, P, and T. And you'll try and see, when I put in the history, why that's happened. Now, again, people have talked about Noether's theorem, and Emily Noether. These symmetries do not, well, of course, some of the clever people in the audience will tell me otherwise, but these symmetries we're talking about here today are not subject to Noether's theorem. These are very different things. These are discrete symmetries. And nonetheless, they still are embedded in the theories of physics. And this is very complicated. I mean, by the 60s, it was known that it's very hard to write down a quantum field theory without them being CPT invariant. I'm not going to go into that because I'm not clever enough to do it, but I'll tell you one of the key predictions is that the mass of a particle and its antiparticle must be exactly the same, and if CP is violated, which Christina will tell you about later, that T is also violated. So this is the history bit of the talk now. I'll try and go quickly so we get there in time for lunch. I've picked out 4 pieces of history. Then I'll move on to the modern experiments. And you will hear about these again, I'm sure, but I think they're of such importance, critical importance, that I do have to mention them. So the first one is the famous Wu experiment. And the background to this was in the early 50s, people thought the parity was conserved in the weak interaction. And to all intents and purposes, what this means, if you have a nucleus, you orientate it, and you look at the way the beta particles come off that. Is it going to be isotropic or non-isotropic? And some people thought it would be, very famously Li and Yang, and other people didn't like any idea of parity breaking. In fact, Landau wrote a paper saying he really didn't like it, that theoretical physics would be a problem if it was broken. But there, interestingly enough, he also proposed something called compound invariance, which we would nowadays recognize as CP and asymmetry. So, on to the famous C violating experiment. This is Madame Wu. I think Christina will tell you about this. You've probably learnt about this in your undergraduate days. What happens is you align it, the decays are not asymmetric. That's a picture of the results. Super nice experiment. and everybody gets very famous afterwards, and we also say the mirror is broken. You know, sort of easily we all say the mirror is broken. That refers to broken symmetries later. You might say this cobalt is very complicated. I don't really know what's going on. You know, I have to think about little balls being, you know, oriented in magnetic fields. Well, these characters, Latham especially, is super famous, and Darwin is famous for being the most important, least famous scientist you've ever heard of. They did a very good experiment where they looked at mu plus and mu minus, and actually a year later, Holt at Liverpool definitively showed that mu pluses and mu minuses also had the same sort of asymmetry in their decay, and that really showed that there was no question of doubt that there was violation of invariance and a charge conjugation. So, step back. What do we know at this point? Well, people believe they knew that strong electromagnetic and weak forces existed. They had studied, at least to some level, CP and CP, and they believed that even though C was broken, CP should probably be conserved. Haven't told you why, but they did believe that. And in fact, some of you may have read or seen or been taught that Feynman gave this famous lecture in which he discussed with his students, you know, if you could communicate to aliens, by which he meant extraterrestrials on the other side of the universe, could you tell whether they were made of matter and antimatter? And he sort of suggested they couldn't. We'll soon see that was not correct. That prediction was not correct. Let me just go on. Because in 1964, as you all probably know, there was a very famous experiment by Fitch and Cronin at Princeton, which was so-called a shocking discovery. Now, why was it a shocking discovery? Because there were no precursive indications, as they famously said in 1980. There were no indication at all that CP should ever be violated. Yet they did an experiment, and yes, the sacred CP was shown to be wrong. Now, if I had a lot of time, I'd explain to you how this would happen. I think Christina, again, will say something about it, but basically there were two particles which looked very similar, the K0. And one was called a K0 short, and one was called a K0 long. And one decayed into 2, and one decayed into 3. The one that decayed into 2 particles decayed very quickly, and the one that decayed into 3 decayed very slowly. And they were supposed to be different CP eigenstates. It's rather too complicated to say exactly why now, especially in a short time. But what they discovered was the one that decayed to 3 very occasionally, if you left it for long enough, would actually decay to 2. And this was unambiguously a sign that CP was being broken, but they could actually really, really measure this. And this gave us a huge blow to the world, because if you imagine you think the CP can't be broken, somebody then says it is. So this immediately made people think that T was now being broken, because there had been a lot of work on CP and T. It wasn't this was a complete vacuum. A lot of these characters have been working on it, and if you look at that name, it's like a who's who of particle physics, of theory in those days. And there's an extremely interesting paper, which I urge you to read if you're interested in this thing, called by Bloom, The Genesis of the CPT Theorem. He goes into what everybody was doing up to that time. And parenthetically, one of the interesting things was it shows how profound and worrying these issues were, because one of the most famous theorists of that time, Pauli, who of course you know what he is responsible for, what you might not know about Pauli was he also wrote to Jung about his dreams, and he dreamed about physics. And very specifically, he dreamed about CPT. At least he wanted to understand where CPT came from. And one of the things that he wrote and tried to interpret with the help of Jung was he dreamt about reflexes, reflections, and being very worried, profoundly worried about this, and a dark woman, and this creating a secret which separates us from other people. And interestingly enough, this secret fills us with fear. So that shows you that's a great line. How we interpret this now, of course, CP and T, and especially Cronin's CP result, getting back onto the main line, is that we have some particle which we'll call K0, which is an S bar and a D, and via the weak interaction, which is that weird little box, the weird little box interaction I have there, it can actually turn it into its antiparticle. And I can have the antiparticle itself, so this quark content here is the same as this quark content on the left. This is an equivalent or mirror-like box diagram. The way we interpret this, the Cronin-Fitch experiment now is this process going from left to right, from particle to antiparticle, and antiparticle-particle does not proceed at the same rate. So K0 to K0 bar is not the same as K bar to K0, which incidentally also solves Feynman's problem with aliens. You can actually talk to an alien on the other side of the universe and decide if they are made of their particles or antiparticles. So what's happening? I've told you what our interpretation is, but can we dig down as to what the physics of this is? And then if we can do that, can we map that onto future experiments to try and understand more about CP violation and CPT? Because what we want to be in the position to do is not simply regurgitate CP violation measurements, but we want to try and look at CPT violating experiments. So by analogy, remember that when an electron goes through a pair of slits, it will interfere with itself. This is a famous thing. We don't want to talk about the philosophy of quantum mechanics here, but it actually goes through both slits. You get multiple diagrams, they interfere with each other, and they produce an interference pattern. Remember, the vacuum is a big, complicated thing. It's not a vacuum is not empty space. All these interactions can happen. So when the K0, when the quarks in the K0 are decaying, they go through possible multiple decay states. These amplitudes can mix, and this mix gives rise to a result that can depend on time, at least microscopically. So this vacuum, this multiplicity of states, these complicated diagrams, give rise to a violation of what looks like a very simple system. And the final bit of our history, because I'll stop the history at this point and I'll move on to what's new, is the CP experiment, which was in the 90s. That's sort of the crowning glory of kaon decay. And this colleague actually wrote his thesis on this experiment, where if you look at this time decay diagram, one for a particle, one for its antiparticle, you can see that very subtly they're different. The blue and the red lines are not quite the same. And this is a little oscillation between the two. It's the difference between matter and antimatter. And in fact, if you're clever enough, you can actually place a limit on the difference between the mass and the mass of the K0 and the mass of its antiparticle, the K0 bar, which is a CPT violating parameter, and you were for the first time making a measurement of CPT. Of course, there's an upper limit because you didn't get a measurement, but the degree to which you can measure delta M to be 0 measures CPT. Just a comment here which you might find interesting. It's only by this point, 2002, if I'm not mistaken, it's only by this point that Greenberg actually shows that Lorentz, under reasonable assumptions, that CPT violation implies Lorentz symmetry. And we'll come back to that statement right at the end. Not least because one way of looking for CPT, you can measure delta M between particle and antiparticles. You can also look for Lorentz violations in your experiments. So current trends, very quickly, just to show you where we're going. History, what are we doing now? So what I want to say is a little bit about the experiments we are doing right now. Christina's doing them, I'm doing them, a lot of our colleagues are doing them. But also, there's some new experiments and also thinking a little bit about the Planck scale. So, as well as K0s mixing, we can do the same things with B quarks. We can produce B0s and B0 bars. We can see how these things mix, just the same way as the kaons. We do this at CERN at the Large Hadron Collider. We heard it talking about the Higgs. We can do the same thing with Bs. We produce huge numbers of Bs, say 10 to the 13. We can do precision measurements with those. We can build fancy detectors, which is what I do. We can build fancy detectors to actually reconstruct these decays. And then when you sift through everything, you can look at an antiparticle on the left and a particle on the right, and you can look at its specific decay modes. And if you look at that orange bump, the key takeaway thing from that is the bump on the left is very different from the bump on the right, and that's the difference between matter and antimatter. It's a huge visible difference. It's not like a little tiny twiddly thing. It's a big difference. And so that's CP. So if you can do something with that, well, first of all, it tells you the T is being violated, but if you can do something clever with that, you can probably say something about CPT. And also, this is just in the second plot because we're quite proud of that. That actually shows you the matter oscillating between matter and antimatter. So you can do all sorts of clever things. Precision is the key. The more precision measurements you make, the more likely you can do to get down to measuring CPT. Now, the problem with all these systems is they're quite complicated. Mesons are complicated systems. Leptons, point-like electrons, are nice and simple. They're point-like particles. They've been known for a long time. I told you very early on, even en passant, that muons played an early role in testing C-symmetry. They certainly did. The famous experiment that I showed you early on from 1957 was actually superseded about 2 months later by another one at Liverpool, which actually measured for the first time a precision measurement of the G-2. What is G-2? It's the precession of the magnetic moment of the lepton in a magnetic field. You may or may not know this. Well, I think you probably do, but leptons have magnetic moments. And these are superbly predicted. These great characters all worked on it. Schwinger has it even written on his tomb. He was so proud of, I always thought it was a bit funny, he wrote that above his wife's name. He had that value of alpha sub S above his wife's name. That's probably not a good move in the long run, especially if there's an afterlife. That'll come back to haunt you. So, I mean, and it's regarded, these predictions are regarded as being the greatest triumph of the Standard Model. So predicting this oscillation, the magnetic dipole moment, are really an amazing piece of physics. And they correspond to complex diagrams like that. And again, if you really want to do this in detail, I don't have time to explain it here, but these differ very subtly from the magnetic moment that you expect. You actually expect the magnetic moment to be related to the number 2, the G factor to be 2. It's actually slightly different. And that is, again, largely due to the fact that the muon is processing in this vacuum and interacting with all the things that can happen. We build new experiments to do this, big precision experiments. We build the detectors for those. And what we find, I'll come back to this in a minute, is we find an oscillation just like they found early on in the 1950s, and we can use that to measure the magnetic dipole moment. And it's different from the Standard Model, but that's another story. Now, just before I tell you why I'm telling you this about the muons, let me just have a parenthesis. These are very hard experiments to do, whether it's LHCb, the KN experiments that Christina will tell you about, or the EDMs. They're super hard. And people have a difference about whether it's worthwhile doing super hard experiments. Pauli thought, the great Pauli thought, if you enjoy doing difficult experiments, you can do them, but it's a waste of time. And this is Pauli tucking into a good lunch like we will in a few minutes in 1934. But others had a different view, and I must say I subscribe to this view, which is also maybe a little bit too easy, that says no experiment is so dumb that it shouldn't be tried. And I think that's a very, very, very different view of how to do physics. Now, as I say, why am I telling you about magnetic dipoles? Because we have a super precise measurement of the magnetic dipole moment. If you can do it for mu plus and mu minus and you see a difference, this principle tells you about CPT. Of course, we can also measure electric dipole moments, which have their own story. Electric dipole moments, this is a famous paper by Purcell and Ramsey. It talked about the intrinsic EDM of fundamental particles. I mean, it was known way back that the EDMs can tell you something important, although they didn't predict whether they'd be 0 or not. They said, the measurement of this becomes purely an experimental matter. But what it is true is if you measure a CP, an EDM, it violates CP, and thence T. And if it violates CP, as you all probably know, this maybe tells you something about the matter-antimatter symmetry. It might not if it's not big enough, but that's certainly one of its motivations to do so. And yet, and again, if you can measure the difference between the EDMs of positive and minus charged particles, that will probably tell you something about CPT. Now, people have done these experiments as well, and are still doing them. This is Jerry Gabriels, who was at Harvard and now is in Northwestern, I think. He's done some of the most amazing experiments ever with electrons. But we're also looking for EDMs with muons. And the experiment that I was telling you about before, we're for the first time taking the measurement of the EDM of the mu plus down to about 10 to the minus 19, 10 to the minus 20. And if you want to look historically where that is, this is a plot of EDM versus year. This is 2020, this is 1900, so people have been looking at this for a long time. But what is interesting is the numbers expected for these fundamental particles are incredibly low, at least for the electrons, they're very low. They're down 10 to the minus 31. Now, the astute of you will notice that there is a standard model prediction for that not being zero, and that's because of vacuum. I will finish in 2 or 3 minutes. There's a prediction for these things not being zero because it's interfering with the vacuum, but nonetheless, that's a very low level. So looking at mu minus, mu plus, EDMs is a critical ingredient to testing CPT, and because they're relatively straightforward particles, their interpretation is a lot easier. If you have this technology, you can even do the EDM of protons and indeed antiprotons using the same argument of particles and antiparticles. You can do the same sort of trick. There are very persuasive arguments why you might want to do these EDMs of protons. Not least, you can this is technical now, but you can at least shed some light on a long-standing problem of CP violation in the strong sector. It may surprise you to know, but some people think it's a bit nasty that the strong theory, the color theory of the strong interaction doesn't exclude CP violation. You have to get rid of it by hand. So if you can measure it in the proton, you're again learning something about CP. So by doing a super precise measurement of protons and antiprotons with an EDM experiment, you're probably going to learn something. So we proposed this some while ago. It's now going to Brookhaven. But to give you an idea about the sensitivity of these measurements, we're trying to measure the EDM of the proton with the equivalent sensitivity of measuring the diameter of the sun to 1/10 of a micron. So these are properly, okay, they're not quite LIGO type of precisions, but they're not bad. And last but not least, I'm sorry for having rushed this, but we do have, not a lot of time. I'm going to tell you something that's entirely speculative, and those of you who are properly theorists can throw bits of furniture at me. But my personal bias is that where you would like to do experiments to understand CPT breaking down is down at the Planck scale. Now, of course, you throw your hands up in horror and say, how do we ever get to the Planck scale? Well, the fact is, if you look in the literature, there are experiments, albeit they somewhat speculative, that allow you to test, for example, the foam-like nature of space and time. The famous theorist Jacob Bekenstein, Wolf Prize medal, had this little experiment where essentially you pass a laser beam or single photons through a glass beam, and you look for anomalous reflection or anomalous refraction, and if you spot some funny effect, then you can A, break Lorentz invariance, and B, you can actually say that space and time are foam-like. Because if space and time are foam-like, and this is me as an experimentalist talking, not as a theorist, there's a pretty good bet you're going to see some Lorentz invariance there, and hence CPD. That's very exciting. There is a route forwards to all these things, not just CP and CPT in the hadron sector, but also way beyond. So, last but not least, I've tried to tell you something about the mirror, the dreams that motivate people to look into that mirror, however frightening they may be. And that's it. Thank you very much.
Thank you very much. We have time for questions.
Oh, that killed it.
Yes? Here. And then we have a second.
I have a question concerning the relationship of parity violation and chemistry.
Uh-huh.
And perhaps there was in history a famous argument since the 19th century that the emergence of life is connected with asymmetry.
Yes,
for example,
exactly.
Pasteur argued in that way. And I remember that there was a discussion of the origin of chirality in chemistry. And that was connected with parity violation. But what I know is that there were experiments, at least in the 1980s, right, concerning measurements of the parity violation energy, because weak forces are involved in chemical bonding, and therefore there was this idea, perhaps we can measure that we had a direct explanation of chirality in physics. But what I know is that these parity violation energy is too small in order to measure it. Do you know something new news about
No,
that?
I don't, but this, of course, Oxford has got a world-class atomic physics group, so if there's anybody from their group there, perhaps they could answer that, right? But I know the same as you. I thought they had actually measured some effect, right? But, you know, if there's somebody from the atomic physics group there, maybe they should answer that. All I could say is that, you know, that we can certainly see it in the subatomic particles, that's clear, right? I mean, the big differences. You should, in principle, be able to see the chirality in something sitting on the bench. But I don't know. So if there's an atomic physicist, help.
Thank you very much. Very interesting talk. So, as we heard so far, it looks like that symmetry is actually just wishful thinking that humans have, because from the very beginning, you know, we start with a symmetrical solar system, we find that's not right, and we have to correct that, and then we carry on. And all the time we're trying to imply symmetry into things because we seem to like it, but it never seems to fit really. So just going back to Professor Mainz's initial question is, you know, is it wishful thinking? Is it human nature to want symmetry and try to force it onto nature? Because what we've heard so far, it doesn't seem to be here.
I agree with you.
Just, before I finish, I just wanted to ask one more question, because you said if we haven't got symmetry in charge of parity, do we? But you said the antiparticles have the same mass. Are we sure of that? Can we be sure that the mass is preserved?
An expert on CPT and field theories will tell you, I think that's one of the predictions of it. That's why you actually measure the mass of the particles and the antiparticles. Now, the arguments of why from, you know, Lagrangian formalization, you insist on CPT, that's that Greenberg paper I referred to. Why that works is honestly beyond me. I don't know, is the answer. A theorist will be able to tell you. Going back to your original comment about symmetry, that's why I like being an experimental physicist, because I like doing the measurements and letting other people worry about how you explain it. It's deeply interesting. It's fascinating. I think humans do have a psychological fascination with this. It motivates everybody, but I personally do not have any kind of prejudice that they should or should not exist. I mean, I've been a graduate student ever since people have been looking for supersymmetry. And that may or may not exist. And I think it's a bad idea to prejudge or put your bias onto measurements. In fact, nowadays, if you were dug into particle physics experiments, everything is, of course, always blinded, which means as far as possible, we try not to put biases into the things we're measuring. So that's my cop-out on that question.
Hi, thank you. That was a really good talk. I actually have a question more related to what you were just saying about measurement and your kind of experimental field than theory, although I am a theorist. How, in terms of probing the space-time foam, as you mentioned, how far away do you think that is? And well,
we did the prototype experiment 3 years ago, right?
Okay.
So it's not very far away. Maybe I might be able to do it later this year. I don't know. If I get the time, I'll do it later this year.
When I see accelerators, like the FCC.
Oh, accelerators! Oh.
Well, when I see accelerators costing as much as the FCC, I then think about where they can go in the future. So if there's already a prototype, then that's understandable. But
the Planck type of experiments, the one I was telling you about foam, is literally a tabletop experiment. You don't have to spend billions to do tabletop experiments. For the other things, if you want to go to higher energies in the classical way, then you get locked into the sort of arguments that you're discussing about big energy, 50-year timescales, blah, to go, 2 orders of magnitude up in energy. I'm not talking about that here. The precision frontier doesn't necessarily require more and more energy. It requires more and more cleverness, generally speaking.
Yes, one.
Just coming back to some earlier comments, the fact that we're occasionally surprised by violations of symmetry principles doesn't mean that the symmetry principles are wishful thinking. And nor does it mean that we somehow impose them on nature. We might like certain symmetry principles, but we have to discover whether nature likes us. And I would say symmetries play an extremely important role in physics. I mean, take, for example, the Lorentzian symmetry, which is the absolute foundation of special relativity in physics, Einstein's theory of relativity. There is no indication that that has been violated. General relativity places a certain qualification to it, but within its within the kinds of experiments you do to test special relativity, Lorentz covariance, the Lorentzian symmetry is fundamental. So is the homogeneity of space, the fact that all experiments done anywhere in the universe should give the same results, given the same initial conditions. The homogeneity of time, these are fundamental symmetries. Nature seems to be saying that they are true, independently of whether we want them to be. So I think, we mustn't lose sight of the fact that the ultimate arbiter is nature, but symmetries play an extremely important role, both in practice and heuristically, in the development of particle physics. Thank you.
I would like to thank you very much for the engaging presentation, and thank you.